Alright, hello and welcome. We've been looking at repeated independent Bernoulli trials, n independent trials of Bernoulli P, the trial. So now we're going to look at what's called the binomial distribution, and this is very important as well. Okay, so here's the definition of binomial NP, which is called the binomial distribution. There are two parameters usually in the binomial distribution. One is the number of independent Bernoulli trials you performed, and P, which is the probability that the Bernoulli trial results in a success. So n is the number of independent Bernoulli trials and P is the probability of success of the Bernoulli trial. And the outcome we are interested in, or B of NP, which we will denote to represent the binomial distribution in some sense, this B of NP is the number of successes. Okay, I'm not interested in anything else. I've done this n independent Bernoulli P trials, and the only outcome I'm interested in now is the number of successes I got. So if you think of the sample space now, what are the various different possible outcomes? You could have 0 successes, 1 success, 2 successes, 3 successes, so on till n successes. So my sample space is just 0, 1 to n. Okay, and here's an example. Okay, so let's immediately begin with an example. Okay, and the interesting simple example is to look at n equals 3. Okay, and B could be 0 or 1 or 2 or 3. And what's the probability that B equals 0? What is the event B equals 0? There are 0 successes when I did 3 Bernoulli P trials. So the trial should result in 0, 0, 0, and that has a probability 1 minus p power 3. We saw this before, right? Now what is the probability that B equals 1? Now the trial can result in either 0, 0, 1 or 0, 1, 0 or 1, 0, 0, and these are disjoint 3 possibilities. Find the probability of each and add, and you get 3p times 1 minus p squared. So likewise, probability of B equals 2 gives you 3b p squared into 1 minus p, and probability of B equals 3 gives you p power 3, right? So that's okay. So there's a bug here. This should be a 1. This is 1. Okay, it's not 0, 0, 0. Okay, so that's the binomial distribution. For small n, it seems very simple. Let's look at one more example, maybe binomial of 5 comma p. Okay, so here I've done 5 trials of Bernoulli P, and I'm interested in B, which is the number of successes in 5 Bernoulli P trials. So probability of B equals 0 is just one outcome, 0, 0, 0, 0, 0, and that's 1 minus p power 5. Now B equals 1 is 5 times p into 1 minus p power 4. Okay, so I have so many bugs in these slides. Hopefully I'm correcting all of them. Okay, so 1 minus p power 4. So probability of B equals 1 is that. B equals 2 will be 10 p squared into 1 minus p power 3. Okay, so you can add it up, all the different possibilities with which you can have 2 successes in 5 trials. Same way, 3 successes in 5 trials is the trials result in 3 ones, and that's the number of favorable outcomes into p power 3 into 1 minus p squared. Why is that? Because each of these favorable outcomes once I have has the same probability, right? P power 3 into 1 minus p squared. So I can simply add up all of them. So I get just 5 choose 3, that's 10. Okay, so you notice how the 5 choose 2 and 5 choose 3 enter the picture. Okay, because I'm only interested in the number of ones that are there in the sequence, and any of these sequences with that many number of ones has the same probability. That's the nice property of this repeated Bernoulli trials, and I can use that, and I get this 10p cubed into 1 minus p squared quite easily. And then for the last one, 4 trials, 4 successes in 5 trials, I get 5c4, which is 5, and then p power 5. Very nice, isn't it? So you can check, like for instance, the probability of B equals 0 plus probability B equals 1 plus probability B equals 2 plus so on should result in 1, isn't it? It's just a sample space with a probability distribution, and if I assign values to that, I should get just 1, and you can check that all these numbers add up to 1. May not be a very easy thing to check. If you've not seen it before, you can add all these guys, it will add up to 1. Okay, so it's an interesting little property also. Okay, so let's see a few more of these cases. We saw just 1 or 2 cases, so let's just look a little bit more elaborately for n equals 1, 2, 3, 4, 5, 6, so that you sort of see a pattern and get used to this, how this is going to work out. So if you look at B equals 0 to B equals 6, for instance, n equals 5, we just saw, I just wrote down all that you would get. For n equals 6, you can see 1 minus p power 6 will be probability of B equals 0. Probability of B equals 1 would be 6p into 1 minus p power 5, right? B equals 1 means 1 success in 6 trials. That can happen in 6 different ways, and the probability of each such thing is p into 1 minus p power 5, because it has one 1 success and 5 failures. Whatever order they occur, each of those outcomes has probability p into 1 minus p power 5, because you can multiply all of them, right? And then how many of them you have? 6, so you can add 6. Likewise for b equals 2, 6 choose 2, 6 choose 2 ends up being 15, so you get 15 p squared to 1 minus p power 4. Likewise for b equals 3, you have 20, b equals 4, you have 15 again, 5 you have 6, and then finally you have p power 6. So you notice the pattern. So I can easily do for n equals 7. So you should be able to go for small n very easily with a table like this. Okay, so that gives you a picture for what happens in a binomial distribution for small n and p. What happens when n goes large? When n goes large, you have to work with the general expression, and the general expression is what I have put down here. Probability that b of np equals k is n choose k times p power k times 1 minus p power n minus k. So this comes out just because every outcome with exactly k ones has the same probability. If you have an outcome sequence which has k ones, k successes out of n, the probability is p power k into 1 minus p power n minus k. Wherever the ones occur, since you multiply all of them together, you have the same probability. So it only matters how many of these sequences have k ones, and that is n choose k. You choose the k positions, make them all 1. So that's n factorial by k factorial into n minus k factorial. So that's the NCK answer. So you see the probability of b of np equals k is this very, very famous formula for binomial distribution, NCK p power k 1 minus p power n minus k. Okay, we have a formula. How does it look? How do you visualize it? You can make these plots. I use some software to create these plots, and here are plots for binomial of n comma 0.5. Okay, so this is plot of that. For n equals 5, for n equals 10, for n equals 20, and for n equals 100. So here are plots of binomial n comma 0.5. So you can see how I've done this. So you can see, for instance, for so you can see what I've done here. I've just plotted for k equals 0, k equals 1, k equals 2, 3, 4, 5, the probability that b equals that k, right? So this is if this is 2, this is the probability that binomial with 5 trials and probability half of success will give you 2 successes, okay, and 3 successes and 4 and 0. And then you go to 10, you see 5 successes, 4 successes, 6 successes, so on. So you see that this is how it works. And as you go to n equals 20, you can see there is a peak at 10, it increases and then decreases again. And you go to n equals 100 also, it has that similar behavior. So even though the plot seems to start at 0, it's not really 0, right? It's half power 100. So half power 100 is really, really, really tiny. So you don't see it here. It's not exactly 0. It's just a very small value, and it goes up to a peak which is attained at 50. Okay, so this is how binomial distribution would look as you keep increasing n, and this is meaningful because in practice you're going to do hundreds of trials, right? So these kind of things are meaningful, and you should get a good grasp of how this distribution looks. So here is a biased distribution. Instead of picking p as 0.5 all the time, let's say we pick p as 0.25, and again I've got okay, so maybe this n is not listed here, so let me just write that down. So this is again n equals 5. I put that down there. This is n equals 10, this is n equals 20, and this is n equals 100. So the n equals 100 case maybe is a bit interesting if you want to look at it. It starts at a very small value and then goes up to a peak around 25 and then falls down and it goes off to a peak, right? So it's interesting that the shape sort of shifts depending on p, and it seems to have interesting behavior. So you can plot these things using mathematical tools, even though the computation might look very complicated, right? So if you look at 100 C25 p power 25 times 1 minus p power 25, it's a very complicated calculation, but it can be done. It comes to about 0.09 or something like that, right? So it's good to see how this calculation works. Okay, so this is how binomial distribution looks. Okay, here are some observations. It starts at 1 minus p power n, okay, and then increases, reaches a peak and falls to p power n again. It starts at 1 minus p power n. As n increases, it's going to be a very low value. It goes to a peak and then falls again to p power n, which is also going to be a very low. Where is the peak? It's roughly around np. Okay, it sort of maybe makes sense why the peak should be around np. There's an exact characterization of where exactly the peak will be, and I'll leave it for you It's an exercise if you're interested. Now, the number of successes can either be 0 or 1 or 2 or 3 or up to n, right? That has to happen with probability 1. So, probability of that is equal to 1. Now, these are all disjoint events. So, you add up all their probability, you should get 1, and that gives you this wonderful binomial identity. It's a very well known identity, 1 minus p power n plus n choose 1 p into 1 minus p whole power n minus 1 plus n choose 2 p squared into 1 minus p power n minus 2. Likewise, if you keep adding all the way up to p power n, you will get 1. Okay, so you can check it for small values of n, and it's an interesting identity to know, and this identity is quite useful when you want to calculate things around binomial distribution. Okay, quick observations about the binomial distribution. Okay, so here is a problem. Okay, so let's try to tackle that. So each person has a disease with probability 0.1 independently in a big population, let's say, and you pick 100 random persons from this population for the disease. What is the probability that 20 persons will test positive? Okay, so now there is a disease and there is a test. Okay, test also sometimes will throw up some false negatives and things like that. So for the purposes of this problem, we'll assume there are no false positives, no false negatives, nothing like that. This test is just a true test. If somebody has a disease, it will come out positive. If someone doesn't have a disease, it will come out negative. Okay, believe me, there are no tests like that, but anyway, we can make that assumption for solving problems. So this is a binomial. So you see that each test is a Bernoulli half trial. Okay, 100. So maybe I should just write what it is. So this is a n equals 100 repetitions of Bernoulli 0.1, isn't it? Right. So n equals 100, and this is p. Okay. And so this question is asking what's the probability that 20 persons will test positive. So that is 100, b of 100 comma 0.1 equals 20, and that is 100 choose 20 times 0.1 power 20 times 0.9, which is 1 minus 0.1, right, power 80. Okay. So what will this number be? It's sort of difficult to maybe compute, but the computer can give you some answers. There are powerful tools. I'll point you to some tools which can calculate these things, and you can get a number. Okay, so I'll leave the numerical value as an exercise for you. You can calculate it. Okay. So it turns out, this is binomial distribution, but maybe what is interesting is something for you to think about. Okay. So instead of knowing 0.1, I may not know the 0.1, right? So there is some probability p with which I'm going to assume that there is this probability that the person has this disease, like this is sort of the incidence of the disease in a population, and I'm going to pick some 100 people and test them, right? And maybe it will turn out that 20 persons are positive. This can happen, isn't it? So now, as a policy planner, I'm interested in what is p, what is the value of p. Okay. So assuming even that the test is very accurate, you don't have to bother about the test being inaccurate. What is the value of p? Okay, so this is an interesting question. Okay, I want you to just think about it. We're not ready to answer this question yet, but these kind of questions is what is interesting in statistical practice, isn't it? So you want to know how will you decide on p? What makes sense? And it turns out there's no one answer to this question. You can come up with multiple ways to answer this question. You will get moderately different answers with different properties, and one studies all that in statistical questions. Okay, so it's an interesting question for you to think about, and this is sort of tightly related to the binomial distribution we will see later in this course. Okay, let's come back to the familiar and simple world of repeated Bernoulli trials and populations computed along and probabilities computed for them. Here's a problem. You have a fair coin and it gets tossed 10 times. What's the probability that the number of heads is a multiple of 3? Okay, so here I have a situation which is a b of 10 comma 0.5, right? I'm interested in probability of b of 10 comma 0.5 belonging to a multiple of 3. So is 0 a multiple of 3? You have to assume 0 is always there. 3, 6, 9, and that's it, right? It can't go outside of that. So that's the probability that b equals 0. So notice I'm going to drop this. So this b is actually b of 10 comma 0.5. I don't need to keep carrying that out around all the time, so I'll just drop it. B equals 3, plus b equals 6 plus b equals 9. Okay, and then that is just 10 choose 0, or it's a fair coin, so half power 10 plus 10 choose 3, half power 10 plus 10 choose 6, half power 10 plus 10 choose 9, half power 10. Okay, so if you want, you can rewrite this as 1 plus 10 choose 3 plus 10 choose 6 plus 10 choose 9 by 2 power 10, and 2 power 10 is 1024. You can write that down, you will get an answer. So that's the probability for the A part. Okay, so B part asks you for probability that the number of heads is even. So you can do it like this if you like, but maybe there is a simpler possibility, I don't know. So this belongs to 0 or 2 or 4 or 6 or 8 or 10, isn't it? So this is the probability that the number of heads is even. So you can use the the uniform distribution. This is will come to our help here. 1 plus 10 choose 2 plus 10 choose 4 plus 10 choose 6 plus 10 choose 8 plus 10 choose 10 divided by 2 power 10. So that will be the answer here. You can quickly evaluate it if you like. You can simplify this and write out an answer. Okay. So that's how you use these Bernoulli trials, and cook up events based on the outcomes and number of heads and number of successes, etc. And then you will get the answer. Okay. Here's another question. This is an interesting little question on communicating bits. Okay. Let's say Alice and Bob are talking to each other, and Alice will send a bit to Bob. A bit is what? Bit is either 0 or 1. Okay. So Alice may send a 0, but it gets flipped when Bob receives it. Okay. Maybe something went wrong in the transmission, whatever. Okay. So that probability is 0.1. So every bit may get flipped with probability 0.1. Use Alice sends a 0, but Bob may receive it as 1 with probability 0.1. Of course, he receives it as 0 itself with probability 0.9. Okay, so that's the picture to keep in mind. And Alice is sending 5 bits independently. What's the probability that at most 2 bits get flipped? So this is a question which involves a b of 5 comma 0.1, and it's asking probability that this is at most 2, meaning 0, 1, 2, isn't it? So this is probability that 5.1 equals 0, that is 1 minus 0.1 power 5 plus 5 choose 1, 0.1 times 1 minus 0.1 power 4 plus 5 choose 2, 0.1 squared, 1 minus 0.1 power 3. Okay, you can go ahead and simplify this if you like, you will get an answer. This is the answer for this question. You should notice how I came up with the b of 5 comma 0.1, right? So this is a situation where there are 5 repeated Bernoulli trials. Each trial has a success of 0.1. What is success for me? See, whatever I am counting is my success. I am counting here that the bit gets flipped. In reality, this might actually be a failure, right? I don't want the bit to be flipped, unless Alice and Bob are fighting or something. But you don't want the bits to get flipped. But nevertheless, whatever you're counting is a success for you in this Bernoulli trial binomial distribution case. So you have to put the success probability as 0.1. So b of 5 comma 0.1 is the binomial under question. So the first step usually in these problems is to identify the binomial distribution in question. Okay. And the next thing is, what is the values taken by that binomial distribution? Once you do that, you can just write it down. Just write it down as different possibilities. You will get the answer. Okay. So the next question is the same thing, but instead of 5, it's 10. Okay. So I'm going to leave this as an exercise to you. So it's very easy. So again, probability that b of 10 comma 0.1 belongs to 0, 1, 2. So you'll get here 0.9 power 10 plus 10 choose 1, which is 10, times 0.1 times 0.9 power 9 plus 10 choose 2, which is 10 into 9 by 2, that's 45. Okay, 0.1 squared times 0.9 power 8. Okay. All right. So this is the value. You can compute these two things and you can compare these two. So you'll see, you know, if you do 10 trials and the probability of success is 0.1, you'll see 0, 1, 2 has a much lesser probability of occurring than you know, 0, 1, 2 with 5 trials. You can compute that and see why that is true. Okay. All right. Or maybe wrong. Maybe I'm wrong. Okay. So check that up and see which is greater. Okay. Maybe you can answer that question. Okay, which is greater? Maybe you can answer that question. Okay, so that's the binomial distribution and simple problems involving binomial distribution. So, like I said, there's always 2 steps: identify the correct parameters for the binomial distribution, identify the values that the problem is asking you to compute probabilities for, and just add it up and get the answer. Okay, all right. So that's binomial for you.